very good windows with the graphene perfect on that window. So it's very good for the students. I had one or two PhD students that made just one or two of these platforms with 1,000 windows, and then he studied all of his PhD using these 2 or 3 fabrication that he did. So statistically, it's very good for the students, right? You don't have to keep doing these windows one by one, and then the graphene breaks and the windows breaks and so on and so on. So this is the macroscopic photo of the platform. We have 1, 2, 3, 4, 5, 6 channels, right? So and each of these channels has 1,000 windows. So it's a very nice buried microfluidic platform, right? Yeah. So this is the SEM pictures of the platform of the buried channel. So now, if you have this thing ready, you need to scoop it up the CVD graphene, right? Remember, you have the CVD graphene with PMMA floating on the water without the copper substrate, right? So you need to scoop it up. So you scoop it up with the platform, and now you have this. You have the PMMA, the graphene covering the windows, right? And now you need to remove the PMMA. After you do that, you need to have your statistically of how many windows you have with the graphene there that hasn't been broken, right? I'll show you later on here, right? So this is just the final, the final slide. So in the end, what you have is this, right? You have the platform, you scoop it up, you have your graphene, you have your electrical contacts, right? So you can apply a voltage and pass a current through while the graphene is in contact with the liquids, and we will drop the liquids on the inlet and outlet. So this is what the membrane looks like, and this is, as I talked to you about a little bit in the beginning of the presentation. So this is the windows, right? So I have 1,000 windows, and you can see here, and I'm not sure about the contrast that you guys are seeing for this one is broken, right? You can see here, this one, the graphene broke. It's just a one atomic thick membrane, so it's very easy to break actually. So this one, it's okay, right? So this one has a little bit of a hole. This one broke. So you need to have this statistically, and then you find your membrane, and then you're going to do your experiment with the very nice membrane that you have, right? But another thing that's important is that when you grow graphene on copper, you have the graphene actually match the morphology of the copper substrate. So if you have a little bit of a hill and the graphene grows on the top of this hill, imagine when you remove the copper, you're going to have something like this, right? You're going to have a ripple, and then this ripple can collapse to a wrinkle, and this wrinkle can fold it into a folded wrinkle. So you can imagine that graphene now is this macroscopically membrane that has a lot of sort of 3D structures, right? You can have some 3D morphology on this 2D membrane, and these folds, ripples, and wrinkles might actually affect the electrical and the mechanical properties of this membrane. And this is something that our study are going to show to you guys, right? So the first thing that we did is what happens when we place the water, right? So what's going to happen with this membrane? So imagine here, now we have the membrane here, and you can see here that we actually placed the wrinkles and the folds. It's actually just like a crumple of paper, right? You have a piece of paper and you crumple it and you stretch it, and this is our membrane, right? It's a crumpled piece of paper, let's say. And then when you place the water and when you drop the water in the inlet and outlet channel, what you see here from the atomic force microscopy profile is that the water actually push the membrane up. It makes a little bit of a pressure, a little bit higher than the atmospheric pressure. It's a little bit positive pressure that actually pushes the graphene up. And imagine, you have a crumpled piece of paper and you have a little bit of a pressure, it's like a small balloon. What's going to happen with this? It's going to unwrinkle, right? It's going to swell a little bit and unwrinkle. And this is the mechanical model that we have of the process of wetting the channels, of placing the water between the channel. As you can see here, this is a little bit of a overdo it, but the membrane becomes less wrinkled and a little bit with the swelling process, right? So this is just Raman spectroscopy, just to make sure that everything is okay. And now you can start with your studies. So one initial study that we did is that we pushed this interface, right? The graphene water interface with an AFM tip, right? To probe the mechanical response of this system, graphene water system. Another thing that you need to remember is that differently from the 3D solids, where when you do this kind of stretching, right, you have Hooke's law and you have a linear behavior. In the case of a 2D membrane, what happens is that this membrane is actually folded on itself, right? So you don't have this linear behavior right away. So initially, right, this linear behavior when you push, let's say, a 3D solid. What happens with your 2D membrane is that the membrane is folded on itself, right? So when you start applying, when you start stretching or applying a force on the membrane, initially you're gonna unfold this folded on itself structure, and then later on that you're gonna reach the regime where you're having this atomic displacement. So what is the message? Is that when you do this force displacement curve, you're not going to find a linear behavior. It's going to be a non-linear behavior, right? And this has been studied a lot, right? And there are some models that describe this, a linear model and a linear component and a cubic component. We have some pretension coefficient, which is actually how this membrane is actually linked with the surface of your substrate. And you have your wrinkled graphene here. And the main point that our results is that this is the result that we have between the dry membrane without water, right? So you have this red curve, and with water, the blue curve. And interesting, what does this mean? This mean here is that the membrane is becoming soft, right? Because initially we are applying the same force, you're actually getting deeper into the material, stretching the material more, right? So initially, this is a very, very strange behavior. Why would the graphene become soft just because of the presence of the water? But if you carefully do a study and you displace the curve, right, you can see here that the intrinsic part of the membrane is the same. Is actually what is happening is that it's just a change on the extrinsic part, on how the membrane actually is linked with the environment in the swelling up. So imagine, if the water just unwrinkles and swallows the membrane, it's expected, right? If you push it down with your AFM probe, what you're doing is just first you need to get all of this water down, and then you're gonna reach the point that you have with your dry membrane, and then you're gonna still push it up. So what we have here in these experiments that the water is actually not changing anything at all about the mechanical properties of the membrane, which is expected. What we're having here is an apparent softness, right? Due to the extrinsic characteristic of the membrane, because it's a crumpled paper, so it has some more material, more skin to move and to swallow, and this let's say extrinsic component is actually performing what is the water is doing, is just changing this extrinsic characteristics of the suspended membrane. So this is some of the stuff that we did some years ago. And now it came a question that I have been asking myself a lot. So the question is, does graphene has any charge transfer with water molecules? Right? So if you do this on a device that I talked to you on the first slide of the presentation, if you have your graphene on a substrate and you have the graphene on the environment, you have water and humidity and so on, you're going to have this charge transfer. But the question is, what is the origin of this charge transfer? It's because of the humidity, but it has something to do with the substrate. So what we try to do here is an experiment of measuring the change in the electrical property of the graphene with in the presence of the water. And with this, we're going to try to understand what is the role of the substrate on this charge transfer problem. So look at what happens. And we have the dry membrane, the wrinkle membrane. We place the water, right? And we do this in real time. So so this part here is the dry membrane. And at this moment, we place the water. And you can see here there's a significant change of the resistance of the material. Almost 20% in resistance variation. It's a very, very high resistance change. And the question is, what is the origin of this really huge resistance variation? Is it because of the charge transfer process or some morphological and mechanical behavior that we know that is going on because we know that the membrane is unwrinkling and swelling up a little bit? And to do that, what we did, we tried to place a substrate on the top of the graphene that we know that it doesn't have any influence on the graphene properties. And it's very well known in literature that the boronatride substrate doesn't have any defects and it's completely inert in terms of affecting the graphene properties. And when we do that, we also did another thing. We constrain mechanically this graphene membrane. So we now have a test experiment that we constrain the graphene in out of plane direction. So we have this mechanical stability of the membrane. And also it's a substrate that we know it doesn't interfere with the electrical properties of the graphene. So we put a lid on the top, right? And now we're going to compare the results of placing the water in the channel with the substrate, with the PN substrate, and without. Let's see what happens. Interesting, look at this. When you have your suspended graphene membrane without the BN, and also we tried with another lid with the PMMA, we have some small variation. So it might be some charge transfer going on here, right? But mainly, this huge variation doesn't happen, right? So this means that we're having some electromechanical effect, right? And if you see, now if you remember Drude's model, now you have the charge carried and a product. The conductivity is a product of the charge carried and mobility, right? And since it's a mechanical issue, right? There is no charge transfer, so we're not changing here. So the only thing that could be changed is the mobility. And how does the mobility could be changed, right? It could be changed because you are actually removing that these folds and wrinkles that actually can act as charge scattering center and affecting the mobility of the membrane. But the main goal of this result is that we are actually demonstrating for the first time that water, the charge transfer between graphene and water is not significant. It might have some charge transfer, which has some prediction, a theoretical prediction, but the main change in this case is the electromechanical effect. So this is what we call a wet resistor, right? So you have this membrane here, which is all wrinkled. When you push the water, it's like a pressure membrane, right? When you place the water, it's unwrinkled. You don't have a resistor variation of the membrane, with almost no significant charge transfer between graphene and water molecule, which was an important result of the literature. So what does it mean? It means that when you make that device, that I talked to a little bit a few times now, is that the charge transfer that we are actually observing is not only because of the graphene and water. The substrate, the silicon dioxide substrate, we also has a lot of defects, is actually affecting the system and producing this charge transfer. So it's not only a charge transfer between the water and graphene. The substrate has a role in this doping of the graphene when you make your device and see the humidity influence of your graphene. The substrate has an influence on that, which is also an important result. And we also, I'm not going to go into a lot of details, but you can also verify the electrical experiment with the Raman experiment. The Raman experiment also are able to decouple strain and doping, and we have done this Raman mapping, and it's consistent with electrical results where you want to have this. If you do a Raman experiment with a wetted membrane and a dry membrane, you're going to see a shift on the center of mass of going on this direction, which is direction of unwrinkling. And if you have any doping, then you're going to see some on this direction, which is minimal. So this Rama experiment also support the electrical experiment, which is also very, very nice, interesting work that we did in terms of understanding the interface and the electrical properties of the graphene with the environment. I'm almost finishing. Now a little bit, some recent results, some recent unpublished results. What we noticed also, this is something that we, let's say, this is an experiment by accident, let's say, right? Is that when we're performing this experiment, right? If you just, you have your graphene membrane here, and if you just let it dry, right? So you're doing your AFM scanning, and if you just let the membrane dry, you're gonna have the surface tension of your membrane is gonna actually pull the graphene down. It's gonna pull the graphene down, the water will dry, and then the graphene will go up again. You can see right here, right? So this is a measurement. Let's say it's not a height and horizontal distance, but it's actually a function of time, right? It's actually scanning the same place. And you can see here that usually the membrane goes down a lot of almost 50 nanometers down. Né? So graphene is really elastic, right? And then it goes up, and the membrane doesn't break. And what we notice is that when you perform this experiment, right? So you have your membrane here. But if you do that with the laser on, right? So you let the membrane dry with the laser on, the membrane breaks. And if you do that, you let it dry, you turn off the laser and let it dry, the membrane doesn't break. So there is a very strange behavior. What does this mean? Is that if you do this process of drying with the laser, there is a coupling of the strain and the laser and the membrane that creates defects that is sufficient for the membrane to break. And this is very puzzling because it doesn't have any temperature, the laser is a low power. So this is what we try to understand at the moment, right? So this is something that we do. You can see here with the laser mapping, right? So all of these results here are when we are doing the laser. So you have the laser on, you place the water, and the water dries, and the membrane dries with the laser, and the membrane breaks. And we try to understand that at the moment. What is that suggests? What is the reason of this mechanism that when you place the laser on, I don't know if you are increasing the Fermi temperature of the electrons, putting a lot of electrons on the conduction band, and this coupling with the strain is creating defects. So we're still trying to understand why this phenomenon is happening. Again, it doesn't happen when the membrane dries with the laser off. It's very puzzling, actually, right? We also see a little bit of this of the defect increasing when we're doing the measurement with the laser, right? So the membrane is wetted, we shine the laser, we do the Rama, and this is proportional to the defect density of the graphene. And you can see that the defect is increasing. But now we turn off the laser and let the membrane dry. And we measure the Rama again, the defect is gone. So we're also seeing another very strange behavior. It's like we are creating defects, right? And then when we shut off the laser and let the membrane dry, we'll have a reversible process after drying. So these are very recent results that we are trying to figure it out. We don't know yet. We think that that has something to do with this population of electrons on the conduction band coupled with the strain. This destabilizes a little bit of the sp2 bonding and enhances the defect creation. But we're still trying to figure out. So just would like to show you guys this because it's a little bit puzzling and very interesting coupling of strain, the membrane, and the wet graphene, the water membrane, and the laser, right? You can actually try to model a little bit of this using some work in the literature. And what we're seeing is that based on the model of this work from Cansado and actually Aldo Jorio, that when you have this vertical increase in the IG over IG, you're actually creating some point defects. So we're able to actually try to, it's a little bit initial results. What we're doing here is a creation of point defects, and if you keep the laser on, it breaks, right? So it destroys the membrane. And if you keep the laser on and you shut the laser off and let it dry, it's reversible. So we are trying, so we can actually identify the kind of defects that the laser coupling with the strain and water is producing, but we are not actually, it's not clear at the moment what is the mechanism of this point defect creation. But it's very interesting results that we are trying to figure out now, doing some simulations. Now we're expanding this study for other 2D materials like molybdenum sulfide, and hopefully we're getting also some very nice results soon. So for this, I conclude my talk. I hope you guys enjoyed and learned something. So we're able to talk a little bit about the application of nanomaterials and this interface, this platform that we're able to produce and to study the interface between graphene and 2D materials. I show you some of the more interesting results in terms of the charge transfer, the electrical properties and the mechanical electrical properties of the graphene membrane, and some more recent results of this coupling of the laser and the water and the strain, which we're still trying to figure out. So thank you, and I'm open for any questions.
Rodrigo, thank you very much. Very nice talk, very inspiring to see that there are so many interesting things. I see that there is someone raising a hand. Where is that? Did someone ask a question? Is it in the... Okay, I will ask a question if anyone wants to. Rafael, go ahead.
Hi, thank you for the talk. I'm afraid that I will steal one of Professor George's questions because he has some works on the Seebeck effect. And when you introduce the laser and raise your electron population, I was wondering whether it could be a Peltier effect in which the PDP induces a temperature gradient. Could it be related to your problem?
It's a very nice question. Usually, I think the graphene membrane doesn't have a very nice, very high Seebeck coefficient. So I don't think it would be significant enough. But it's a good question, right? It's a good point, right?
Okay, thank you.
Okay, any other questions? Is anyone raise a hand? No. Okay, I have a couple of questions. In the beginning of your talk, you mentioned about meter scale graphene. So can you talk a little bit about how do you get that, and what use do you have for that?
So usually this meter size is a roll-up system, right? Okay. So you have your copper substrate which is rolling, right? So the graphene is, you have your gas meets this copper roll, right? And it spins and go, and then you have to maximize your size, right? Because some of the applications that I'm not quite sure what kind of application is doing now, right? But it's one, it's for transparent conductor, right? So just the touch screen, because the graphene is actually transparent and is a conductor. Some of the applications that I think Samsung has in terms of telephones, of iPhones and mobiles, is actually to make this transparent conductor, right? So it doesn't have to be very high.
Screen.
Yeah.
For screens, okay.
So it's basically, I think, for this kind of application would be touch screen, right? So a transparent,
which is it's a huge market, right?
A huge market, yeah.
It's a huge market.
Yeah, but all of this is all is a little bit weird. So we don't know. Samsung says, okay, we have already commercial phones with graphene, so we don't actually know if it's actually commercial or not, right? So
Okay.
this is what we hear, right? So it's for it says that there are already some commercial mobile phones with the graphene as a transfer conductor.
Okay. Okay. Well, one question I had was the dimension of that Berry channel, but I saw in one of the slides it was 10 across, 10 microns across.
Yeah, it's 10 to 50 microns, right? Around
Okay.
the windows are fixed, right? So the Berry channels goes from 10 to 50 microns, but the windows are fixed. So the windows are 3, 4, and 5 microns, 5 by 5, 4 by 4, 3 by 3, right? So, so the windows are fixed. It's a problem, right? If the windows is too large, the membrane breaks easily. So it's not so easy to make a mechanically stable membranes without any tears. So 3, 4, and 5 microns. Above 5, it's hard. It's hard to be hard.
Yeah, it's funny that you say that because I have gone to, well, no, actually, you know Eva Andre?
Yes.
Yeah, she's very famous, right? From Rutgers. Yeah, she does a lot of experiments. I went to a talk by her where she said, well, if we put a monoplane of graphene as the floor of this lecture room, we could sit all of you on top of this graphene monolayer and it wouldn't break. But then you say that if you increase a little bit the window, it's gonna break because of its own weight.
I think it's let's say.
So I was not sure what she was talking about.
I think this is over, let's say, how do you say, right? Because microscopically, right, it's really hard, but it was an atomic plane, right? So you need a little, any string, it breaks, right? Because it's two atoms, right? So, I mean, I think she's just trying to make it maybe a figure of speech, right? So if it's, right?
Yeah, if you make a very, very tiny thing, it's very strong.
Yeah.
But if it's big, it's going to collapse under its own weight. That's the message. Okay.
Yeah.
The other thing you said that you play the carbons with the evaporation of carbons, they go on the copper surface, and but then you said that you actually have to put the PMMA on top. So how much of the copper do the carbons see if there is PMMA on top?
The PMMA is just after growth.
It's after. Okay.
It's just for your membrane to be mechanically stable when you remove the copper. That's right? Because otherwise, it's the same problem. It's the same problem, right? You have your atomic plane graphene. If you have this without the copper, it's gonna break.
Okay.
If you do this, if you etch your graphene, right? So the growth is this, right? So it doesn't have any PMMA. You just have your beautiful of the copper. But if you remove the copper, this will break. It's gonna be some small.
The large scale structure of the graphene is maintained by the PMMA.
Is by the PMMA, yeah. So after you transfer, the substrate is the one that becomes mechanically stable, right? And then you remove your PMMA. So you can remove your PMMA afterwards, right? In the end.
Okay. Now I understand.
Yeah. The last step, you remove your PMMA. That's why it's difficult to make large windows. People has already made 1 millimeter.
The PMMA is on top of graphene.
Yeah.
On top. I thought it was between the graphene and the copper. No. That wouldn't make sense. Wouldn't make sense. Yeah. Right.
People are able
you are like doing like that, right?
Yeah. The record of suspended graphene membranes it's 1 millimeter. Which is I couldn't imagine having a 1 millimeter square suspended graphene membrane. Like people has already done. So if you can think of suspended graphene membrane, people has already done 1 millimeter square.
That's
It's
the
really
that's the record.
I couldn't. I was never able to do it above 10 microns.
Okay, no, that's probably very hard.
Yeah.
So you mentioned that the exfoliated graphene is the best graphene that you can get because it's clean, no defects and everything. So why not do exfoliate graphene for everything?
Because
Is
it's
there a
hard.
limit on the size?
It's hard. It's hard, right? You're gonna keep exfoliating with your tape, then you're gonna map.
Okay.
You're gonna find 3 in your
So there is no
scale. You're gonna find 3 or 4 flakes, and the size is not so much, right? The size is small, and so it's. I mean,
but there is no robot that you can.
People in Manchester are doing that, right? But it's not.
Okay, doing robots. Okay.
It depends on the application that you want, right? Some application you can actually.
It's expensive. Very expensive.
Yeah, but at some point you can actually for the point is for you do this ultra sophisticated mesoscopic physics, right? With the tricytronic and everything. People are doing that, right? They put the BN, put the graphene on top, put something layer by layer, do whatever you want with this Lego structure, right? So they do this for more basic stuff. For applied stuff, it depends on the application. If it's expensive enough, you can expend your time and build this, and it's okay. You can do it, right?
You're gonna recover your money, right? The money that you invested. Okay.
Yeah, exactly.
No, it makes sense.
Yeah.
And the other question I had, you answered it. You said that I was wondering what kind of defects are created by the, and you said that are point defects, right? Are vacancies, substituted impurities,
I think it's
so on and so forth.
Yeah. So, I mean, we don't have a direct evidence, right? We're using the model that Cansado and Jorge did, but the curve actually follows the same trend that, because in their study, they actually have done this on purpose, right? They create with a E-beam and then perform the simulation and the model. So they have a very nice model of this behavior, point defects, if it goes perfectly. So our Rama behavior matches their behavior. So we're assuming that it's point at maybe vacancies, line point defect. When I'm calling point defects, I think it's vacancies, right? Carbon missing carbon.
Okay.
Yeah.
So so we have some theorists here. How can you model that using molecular dynamics or DFT? What would be
what we're doing now with our theoretical partners here is that it's a DFT. It's a large DFT, right? I think it's possible to use. It's the large DFT that you can get, right? And then it's actually increasing the Fermi temperature of the system to simulate the light absorption and applying the strain. So the simulation that we're having that's actually providing some consistent results, right? So depending on this Fermi temperature and how much the membrane is stressed, you start to have defects showing up in this DFT simulations. So that's the closest model that we have at the moment, increasing the Fermi temperature and pushing the graphene and seeing that the DFT does his job.
So it's DFT, not molecular dynamics. It's
no, I think they've done some
lower energy scale.
Yeah, but it's I think they can do this. I'm not sure how many atoms now, but the system is increasing.
It's probably you need a huge computer.
Yeah,
really big computer. Yeah. So we have some DFT specialists here. So if they want to put their 10 cents in this story.
Yeah.
So Rodrigo, it was very nice having you here. I thank you very much for accepting our invitation. I will be writing you an email to ask for the slides if you don't have any problem with there is no unpublished results or something like that. And we post the slides with the video.
Okay. Thanks a lot.
Okay, and we hope that we will meet at some conference, or you will come here to Berlândia to talk to us.
Sure.
You are doing very, very interesting stuff.
It will be a pleasure. Thanks a lot for the.
Okay, thank you. Thank you very much. Nice to meet you.
Thank you. Thank you.
Thank you. Bye-bye.
Bye.